Now that we have introduced the natural logarithm function as the antiderivative of 1 over x that takes a value 0 at 1, we want to introduce the natural exponential. The way we're going to do that is as the inverse function of the natural logarithm. So before we do that, we're going to open a long parenthesis on one-to-one functions and inverse functions, so to make it clear what we're talking about when we talk about inverse functions. So to start with, just to argue on an example, let's think about motion along a straight line. So if we have a particle moving along a straight line, like this one, we're going to give an orientation to this line, so there's a positive direction of motion. And if we want to locate the particle at a certain time, we need to do that with respect to an origin. So we fix an arbitrary origin, and we have a unit of length to measure position on this line, and therefore we can give the position of the particle at any time. So if, for instance, a particle is here and is moving along the straight line, it can move in one direction or the other. Let's say it's in this position at time t, we can give this position as a single number, f of t, which corresponds to the sine distance to the origin. So in this case, f of t would be a certain number of unit of length away from the origin on the left, and therefore the f of t would be negative. So let's say we have our particle moving along this straight line, and we take some measurements at certain times. So let's say at time t equals 0, it is 2 meters on the right of the origin. So f of t would be 2. After 1 second, it's 5 meters away on the right. After 2 seconds, 7 meters away on the right. After 5 seconds, 15 meters away on the right. So if now, instead of looking at the position given the time, which clearly here defines a function of time, we are looking at a given position and trying to see at what time the particle is in that position. So if the position is s, well, if we just turn around the measurement we had, for position 2, the only time that we have measured, at least, where the particle is in that position is 0. For position 5, the only time where the particle is in that position is after 1 second, and so on. However, if we add one of the measurements, if we add another measurement, and after, say, 8 seconds, we measure the position, and it is 7 meters away on the right of the origin, then when we turn things around and ask, given a position, at what time or times is the particle in that position, we see that for position 7, there are 2 different times corresponding to it. So that means 2, 7, I associate 2 times, it's no longer a function. So turning the relationship around may or may not give us a function, even if we start from the function f of t that associates 2 times its position. That's a well-defined function. When we turn things around and try to associate time to position, it may or may not be a function. Let me try to represent the same situation differently, maybe to try to clarify this. So here is our function position in terms of time, and we can represent it that way, where the arrows represent how f assigns a position to a time. So f of 0 is 2, f of 1 is 5, f of 2 is 7, and so on. So now, if I look at the inverse relation, that is, given a position, I want to know at what time the particle is in that position, that corresponds to turning the arrows around. So to 2 now I associate the time 0, to 5 the time 1, and so on. If we go back to the first relation, position in terms of time, and we add the additional measurement, that at time 8 the position is 7, then this is the new situation. Now we have 2 arrows that point to the position 7. So if we go back to the inverse relation, that means we are turning the arrows around. Now we're in this situation where, in particular, from the position 7 comes out 2 arrows. And that means this is not a function because to 7 we associate different values. Okay, so this was the type of situations that led to a problem when we turn arrows around. Right? If we have 2 arrows that arrive at the same point, and when we turn them around, we have 2 arrows coming out of the same value, and then that's no longer a function. So we want to look at the functions where we're not going to have this problem. In other words, where when I turn the arrows around, I'm not going to have 2 arrows coming out of the same value. And that leads to the definition of a one-to-one function. The function is one-to-one if it never takes on the same value twice. In other words, if we don't have this situation of 2 arrows leading to the same value. So formally, that means that if I take 2 numbers x1, x2 in the domain, plug them in the function f, it returns different values of f. Or equivalently, the only way I can get f of x1 equal f of x2 is if x1 is equal to x2. So graphically, what does that mean? Let's look at this function, for instance. And we can ask the question, is that a one-to-one function? Well, let's look at an horizontal line y equals c. And here we see that this horizontal line intersects a graph in more than one place, specifically in 3 places. And look at the x-coordinates of these 3 intersection points. We have x1, x2, x3. If you plug these values in the function f, it's going to return c each time. In other words, f of x1 equal f of x2 equal f of x3, and in that case equal c. So that means I have several x values that are sent to the same y value. In other words, this is not a one-to-one function. Let's look at this function now, and let's try to use the same kind of reasoning. Y equals c intersects the graph y equal f of x in one point here, and so the corresponding x-coordinate of the intersection point is sent by f to c, but this is the only such x that is sent to c. But here you see that if I move around my horizontal line, I have the same property. In other words, the horizontal line intersects the graph in at most one point, and that means this one point is the only one that can be sent to the value c. Then in that case, of course, I'm never going to send 2 different x's to the same value y by f, and therefore the function is going to be one-to-one. So this observation is often referred to as the horizontal line test, which states that a function is one-to-one if and only if no horizontal line intersects its graph more than once. So this is what we have looked at. So for instance, if we look at the square function on the real line, it's not one-to-one, as you can tell from the picture, or simply, for instance, by observing that if f of x is x squared and defined on the real line, then f of -1 and f of 1 are both 1, so I have 2 different values sent to the same y value, and therefore it's not one-to-one. But one thing that you may observe is that if you take the restriction to 0 infinity, for instance, then that means you forget about this part of the graph, and now you see that the corresponding graph passes the horizontal line test. The intersection with an horizontal line is going to be either 1 point or 0 points, if y is a negative constant. And so this is now a one-to-one function. So really, when we are talking about one-to-one, we should specify on what interval. Y equal x cubed, on the other hand, as you can see here, is an increasing function and passes the horizontal line test, and therefore is a one-to-one function on the entire real line. Now, one thing that I'm not going to justify formally, even though it wouldn't be that hard to do, but that you can probably guess from these pictures, is that if you have a function that is increasing on a certain interval, then it should be one-to-one on that interval. And similarly, if it's decreasing on a given interval, then it should be one-to-one on that interval. But when you have changes of increase and decrease, then we begin to have some problems. So the proposition here, some sort of criterion, is that if a function is monotone, in other words, either increasing on the interval I or decreasing on the interval I, then f is 1 to 1 on that interval I. So now let's go back to the problem of inverse function. Now if we have a 1 to 1 function with domain A and range B, by range here I mean all the values that are obtained as values of the function f. So values that the function f takes. So we have a situation like that. F goes from A to B, and B is the range. In other words, if I pick a y in the set B, then it is a value that the function f takes. In other words, there is an x in A that is mapped on y. But the function is 1 to 1, and therefore there is at most one x that is sent to a given value. So that means this x that is mapped on y is unique. In other words, if I take y, there is a unique x in A that is mapped on y. That means I have a function relation that associates to y the unique x that I will denote f inverse of y, where f inverse in symbol is an exponent -1, and x is the unique value in A that is sent on y by f. So if I have a 1 to 1 function from A to B, I have an inverse function from B to A that undoes what f does. More formally, if f is 1 to 1 with domain A and range B, then it has an inverse function that we will denote f to the exponent -1, and I will read that f inverse, whose domain is B and range is A. In other words, the domain is the range of f, and the range is the domain of f, and it is simply defined by f inverse of y is x if and only if f of x is y, and that's for any y in B. Now, almost by definition, you see that if you plug f of x in f inverse, where x is some point in the domain of f, then you obtain x. And similarly, if y is in B, in the range of f, then if you plug y in f inverse and then plug the result in f, you're going to get back to y. So in other words, what f does is undone by f inverse, and what f inverse does is undone by f. So this is our definition of the inverse function. And you see that this condition of f being 1 to 1 is necessary for this to make sense, as we have seen at the beginning. One last comment before we turn to the next video about the notation f inverse with a -1 exponent. Note that this notation f to the -1 of x is not the same as f of x to the -1. In this context, where the exponent -1 is next to the function, it indicates the exponent -1 indicates the inverse function. So that's the inverse for composition of functions. On the other end, on the left-hand side, we have f of x, which is a number, because I have plugged a certain value of x in f, so it returns a number, and I take power -1 for that. Then the convention for the power -1 next to a number, let's say 3 to the -1, is 1/3. Right? So here the -1 as an exponent stands for the multiplicative inverse. It's the inverse for the multiplication law, as opposed to the composition law for functions. So this would be just 1 over f of x. So it's important that you remember that this exponent -1 does not stand for the same thing if it's next to the function, or outside like we have on the left hand side if it stands next to a number. So now turn to the next video to see more about inverse functions.